Welcome to Lecture 9. In this lecture, we're going to talk about the electric field, which explains where the electric force comes from. Now that we've finished Coulomb's law, we know that there is an electric force between any two charged objects. A good question is, what's the agent of the force? What makes the electric force? To think about that, let's go back to gravity for a minute. We know all objects with mass feel a force due to gravity. We call that force the weight in physics 1050 or 1020. So we know a force due to gravity or weight is mass times gravity. When we asked what the agent of that force was back in physics 1020 or 1050, we said the Earth. We said the Earth makes the force. But how does that work? Well, around every massive object, there exists what's called a gravitational field G. That gravitational field permeates all space and actually changes the shape of space. If you're interested in that idea, you might like A Brief History of Time by Stephen Hawking. It's a real good book. So if the force due to gravity is m times g, then g is the force per unit mass, and that's called a gravitational field. Any object with mass m, which is in a gravitational field g, is going to feel a force due to gravity equal the mass times that field. So the gravitational field g is the actual agent of the force due to gravity. The force is exerted through that field. Our treatment of electric forces is exactly the same. A charged particle Q will feel an electric force due to an electric field. So we can say that an electric force is charge times an electric field. So if we put any charged object in an electric field, it will feel an electric force. So an electric field could be thought of as the electric force per unit charge. So what makes an electric field? Just like the Earth, or an object with mass, or a large mass, makes a gravitational field around it, and a smaller mass, like an apple, feels a force, then a big charge, called a source charge, that makes an electric field, and a little charge, sometimes called a test charge or a probe charge, feels the force. Our electric field has a symbol of E, and the units of electric field are newtons per coulomb, N over C, or, and we'll talk about this more later, volts per meter. So let's flesh out that idea and the definitions a little bit more. Let's say we place a test charge, and generally we'll represent our test charge by a symbol of a lowercase q. And our test charges are very small charges, and they're positive charges. Let's put a small test charge at some point in space. Then let's ask the question, does it feel an electric force? So does it feel that electric force that we described, say, by Coulomb's law? If the answer is yes, then we would have our little test charge here. It would feel an electric force, say that points this way. If it does feel that electric force, then it must be in an electric field. So the definition of our electric field is that electric field is the force per unit charge. Or the electric force per unit charge. That's the definition in words. In terms of a symbol, E is the electric force divided by Q. So we could draw our electric field on this picture. It would be that force divided by our test charge, Q. So our electric field would look something like this. The units of electric field are newtons per coulomb or volts per meter. The magnitude of the electric field is sometimes called the electric field strength. And then some tips that are just good to know is that our electric field is created by a source charge, capital Q. Okay, so our test charge is small q, our source charge is big Q. Um, the electric field, this is an important idea. If we think about the gravitational field, so if we hold an apple up in the air and we let it go, it will still fall down. What if we didn't have an apple? Does gravity still exist? Well, yes, of course it does. Same thing is true with electric fields. So the electric field is there even if our test charge Q is removed.
It's 11:15 a.m.
Oh, there's my alarm going off. Okay, and then the last thing is that the electric field, since it's made by the source charge, capital Q, it does not depend on the test charge, little q. So here's a summary about our electric field. The electric force on a charge is exerted by the electric field. That means the electric field is the agent of the electric force. The electric field is created by source charges, usually represented with a capital Q. Electric forces and fields are vectors. That means whenever you do an electric field or force problem, you'll give an answer with a magnitude and direction or in unit vector notation. The relationship between electric force and electric field is that electric field is electric force divided by the test charge Q, or the electric force is the charge in the field times the field itself. One thing that's important here is you include the sign of the charge Q. So the sign of the charge matters. Electric field exists at all points in space, just like gravity exists everywhere in space. A charge does not feel its own field, just like the Earth doesn't feel a gravitational force due to the Earth. A capital charge Q makes an electric field, but it doesn't feel that electric field. And then there's this last bit, which is pretty important. The force on a positive charge is the same direction as the electric field, and the force on a negative charge is opposite the direction of the field. And that comes from our expression for force and field here. So let's go through a quickie example. If we put in a coordinate system, x and y, and if we have an electric field and we place a little charge q in that electric field, then we'll say that our electric field, it points to the right. It has some magnitude with a direction to the right. Our electric force is the charge, which is Q, times the electric field. So there's our vector. So that's Q times E in the I hat direction. So this electric force is to the right because it's positive I hat. So F and E, same direction. But if our charge is negative, let's say we have a charge of minus Q instead, our electric field still points to the right. This time our electric force is our charge, minus Q, times our electric field, gives us minus Q E I hat. Since it's the minus I hat, this one points to the left. And our positive charge had a force towards the right, points to the left. So this tells us that if the charge is negative, the force and the field are in opposite directions. So you can always show that's true with the math, or you may just remember that. For an example now, we'll go back to an example we did earlier. We had 4 charges, and we had labeled those Q1, Q2, Q3, and Q4. And at the center of that square, we had a little electron, and we calculated the force on that electron. So we said that force 1 was towards charge 1, force 2 was this way, force 3 was this way, force 4 was this way, and we found the net force on that electron to point straight up. Okay, we did a vector addition. The electron felt the force due to charge 1, charge 2, charge 3, and charge 4. So that was something we did. Now let's ask, what is the electric field at the center of the square? So Q1, 2, 3, and 4, those are all source charges. They all make electric fields. And the reason that the electron felt an electric force is because it was sitting in the electric field created by these four charges. So can we find that electric field? Turns out there's two ways to do it. There's a hard way and an easy way. I'm going to do the easy way here and we'll come back around to the hard way in a few minutes. So the easy way is to remember that electric field is the electric force per unit charge. And our unit charge here is the charge that's placed at the center of the square that's feeling the electric force. That would be the electron. Okay, so the four source charges, 1, 2, 3, and 4, they make the electric field. The electron feels the force. That's probably worth a note, actually. So the electric field is made by Q1, Q2, Q3, Q4. The electric force is felt by the electron at the center. It's really important to get these concepts down before we get too far into it. So the electric force was 8.14 times 10 to the minus 11 newtons, J hat, divided by the charge on an electron, which we remember is minus 1.6 times 10 to the minus 19 coulombs. Put that through the calculator, and what we get for our electric field is minus 5.09 times 10 to the 8 newtons per coulomb, J hat. Okay, some things we'll point out here. You see that the electric field has a J hat in it. So that's a reminder that electric field is a vector, so it includes direction. What else? Our electron has a negative charge, so the force and the field have opposite direction. So electron is negative, therefore force and field are opposite. Okay, and let's just add in the little note that these guys are vectors. Really important. Sometimes we forget which are vectors and which are scalars. Okay, and then the last thing we'll just remind ourselves is that this electric field doesn't depend on the electron at all. So it doesn't matter about the electron. Whether this electron is here or not, this electric field will still exist. That's because the electric field is made by these four source charges. So that electric field doesn't depend on the electron. Let's do one more example the easy way before we go on to talk about what do I mean by the hard way. Let's say that we have an equilateral triangle of side length 1 millimeter. At the bottom two corners of the triangle, we have a plus 1 microcoulomb charge and a minus 1 microcoulomb charge. We'd like to find the electric field here at point P. So some things to notice about this diagram is that there is nothing here at point P. Okay, that's just an empty spot in space. Plus Q and minus Q, those are what we call source charges. They make an electric field. Now, if we put a charge at point P, it would feel a force because it would be sitting in an electric field. And you may recall that we actually did that example. So we put a 0.5 microcoulomb charge at this point, and it felt an electric force, which we found to be 4,495 newtons, and we found that by doing a vector addition. So this little plus charge Q right here, now in context, that's our probe charge or our test charge. So let's see if we can use this force and this probe charge, this test charge, to find the electric field that must be at this point. So let's remember the relationship. Electric field E is the net force that acts on some sort of test charge divided by the test charge itself. And in our previous problem, we had a test charge here equals 0.5 microcoulombs. So our electric force was 4,495 newtons in the I hat direction, and our probe charge was 0.5 microcoulombs, or 0.5 times 10 to the minus 6 coulombs. That gives us an electric field of 8.99 times 10 to the 9 newtons per coulomb in the I direction. So our net force was to the right, and our net electric field is to the right. Those guys are parallel because our probe charge or our test charge is positive.